Welcome to Math with Mrs. Bibb. Today we will be discussing shapes of graphs, sketching graphs, and comparing functions. The first thing we will define is a line of symmetry, and we're talking about a line of symmetry in the y-axis. Or some other vertical line in which this line cuts a graph exactly in half, where one side matches the other side. Let's look at some graphs. We want to decide if this graph has line symmetry, either in the y-axis, so let me highlight quickly, either in the y-axis or some other vertical line. So let's look through here and let's see if we think that these graphs have symmetry in the y-axis. So if I look at this first one, if I were to fold this graph in half, let me grab my pointer. If I were to fold this graph along this line, and this would be where the fold is at, would this piece land on this one? And no, it would not. So that one does not have symmetry here with the y-axis. Does this graph have symmetry with the y-axis? Hopefully you can look at that and see if you fold it along the y-axis, definitely this part would be way over here, not overlapping here. And same thing with this. If I folded it along this blue line, then it does not have symmetry. And same thing with this. So none of those have symmetry with the y-axis. So let's look and see if there's symmetry with any other vertical line. So what that means is look at x equals 1, x equals 2, x equals 3, x equals 4, or negative 1, negative 2, negative 3, negative 4. Could you fold along those lines and produce the exact same graph on each side? And hopefully when you look at the first one, you see no, there's no line symmetry for this first one. How about the second one? If I drew a vertical line here, no. Here, no. How about here? If I drew a vertical line at x equals 1.5 and folded along that vertical line, wouldn't this match this? And same as this piece here, match this piece? Yes, it does have line symmetry. At x equals 1.5. So the vertical line x equals 1.5 is where the symmetry occurs, the line symmetry. Okay, let's look at the next one. Obviously, we said no for here for the y-axis. How about here at x equals negative 1? No. How about at x equals negative 2? Yes. If you folded that curve along this vertical line, this curve and this curve would match. So yes, it has line symmetry. At x equals negative 2. And then let's look at the last one. Could you draw a vertical line and fold it and have the same graph on each side? And that answer is no. There's no line symmetry here. Next, we're going to write down some definitions. We're going to write down definitions for increasing, decreasing, extrema, relative minimum, relative maximum. So increasing. Increasing is where the graph goes up, where a graph goes up. Decreasing then would be where the graph goes down. And both of these, it's as you are viewing that graph from left to right. Just like you read a sentence, you're reading that graph from left to right. Extrema. Relatively high or relatively low function values are called extrema. So I'm going to put relatively high points on a graph. So relatively low points are called a relative minimum, and a relative minimum occurs when no other points nearby have a lesser y-coordinate. And then the relative maximum occurs when no other points nearby have a higher y-coordinate, or greater, have a greater y-coordinate. I have also seen them called local maximum, local minimums. So that's the extrema that we will be discussing. Determine the extrema of f of x, then identify each point as a relative maximum or a relative minimum. So as I look at this graph, I'm looking for high and low points on the graph. So I want to outline something too. I'm going to highlight. So I'm reading this graph from left to right. This graph is increasing because it's going up, and then it starts decreasing because it's going down, then it's increasing again. So increasing is yellow, decreasing is green, increasing is yellow. So that's where what it means by increasing and decreasing. And where it changes from increasing to decreasing or decreasing to increasing, that is where your relative maximum or relative minimum values occur. Make sure you use your brain. If it's at a highest point, this is a relative maximum. And if it's at a lowest point, then this is a relative minimum. Now, what they want us to do here is they want us to actually name, I was going to say name the order of pairs, but no, they want us to talk about the fact that B is a relative maximum. We don't have to list it in order of pairs. And then C is a relative minimum. Okay. Here's like a real world example. And it's asking us to look at the graph and look at the paragraph. A comic book store uses a function to model its profit in thousands of dollars, given the price in dollars that it charges for individual issues. Determine whether point D is a relative minimum, a relative maximum, or neither. Then interpret its meaning in the context of this situation. So point D, is that a relative high point or a relative low point? So hopefully when you look at that, you can tell that D is a relative maximum. And then it is showing me point D. If you look at this, your x-axis is your cost per issue. So we're looking at about a $4 cost per issue. And your y-axis is earnings in thousands of dollars. So at $4 at a cost per issue, the profit would be about $80,000. So I don't think they want us to get that specific though. Point D represents, is what we're going to write, the greatest profit the comic book store can earn given the price it charges per issue. And I got very specific there earlier. That is what that relative maximum value represents. Example 4, aerobatics is what this is. It's called stunt flying. It's the practice of intentional maneuvers of an aircraft that are not necessary for normal flight. Lincoln Beechey, an inventor of aerobatics, was known for his stunt called the Dip of Death, in which his plane would plummet toward the ground from 5,000 feet until he leveled the plane. His distance from the ground during the stunt can be approximately modeled by the function f of x. Identify any extrema in the context of the situation. So point A represents that at about 20 seconds, Lincoln Beechey reached a what relative maximum in height at 5,000 feet. So let's see what goes there. At 20 seconds, Lincoln Beechey reached a blank relative maximum in height at 5,000 feet. I got this example from the textbook, and it seems as if they have, and you can mark this out, they have answered this question for you. Reached a relative maximum in height at 5,000 feet. Since there's no other point higher around point A, then point A would be called a relative maximum. After point A, his height is, and they did it again. So can you tell this is his height? What's happening to his height here? It is decreasing until he levels out the plane. So scribble that out. The answer is decreasing there. I'm sorry about that. I should have read that example more closely. In behavior, we're going to define in behavior. In behavior describes the values of a function at the positive and negative extremes in its domain. So let me draw, and hopefully you have room to draw this. And if you have a highlighter, grab a highlighter. If you don't have a highlighter, you might want to highlight this when you get to the classroom, because I think it's very important to see this highlighted. So as our X value is increasing, as it's getting more positive and more positive, end behavior will be written like this. As X increases, you are trying to figure out what Y is doing. So as your X value is increasing, your Y is either going to be increasing, the end of your Y will be here in the first quadrant, or it will be decreasing, your end of your Y will be in the fourth quadrant. So just to name those quadrants really quickly: first, second, third, fourth quadrant. So as your X is increasing, so as X is increasing, what is your Y doing? If it's pointing up, then it's going to, in quadrant 1, then it's going to be increasing. Or if it's pointing down, it's going to be decreasing. So that blank that I left over there, you'll either put increasing or decreasing in that blank. Now let's go back to the graph. As X is decreasing, so as X decreases, we have to figure out what Y is doing. Is it increasing or decreasing? So as we're looking to the left of the origin, we are trying to figure out if our end of our graph is going to upwards in the second quadrant or downwards in the third quadrant. So again, in that blank over there, we'll either put increases or decreases based on the actual end behavior of the graph. So we're going to determine the end behavior of both of these, and we'll call both of these f of x. So the first thing I want to point out is you're going to have, and I need to get rid of that highlighter. You're going to have as x increases, comma, y, and then we're going to fill in the blank. And then you're going to have as x decreases, comma, y, then we have to figure out what y is doing. So let's do that now. As x is increasing, so I'm looking at this x-axis, what is our end doing? Our end is going up. So that means our y is increasing. So as x increases, y increases. And let's look on the other side. As x decreases, what's our y doing? Our y is going down, which is also decreasing, so y decreases. And it's solely based on this end. This end is going down, so that's decreases. This end is going up, so that's increases. And let's write what we need for the next question. As x increases, we have to figure out what y is doing. And as x decreases, we have to figure out what y is doing. Okay, so let's look at the graph. As x increases, that end is going up, so then that means y is increasing. So as x increases, y increases. And as x decreases, I should have found another graph. As x decreases, what's y doing? It's also decreasing. I'll draw us another graph, so if you'll please draw this graph too. And it can be small. I think you have space. Let me look at your paper. Yes, you'll have space right beside of that last graph to draw this one. So let's draw Let's draw this graph right here. Draw your y-axis and your x-axis, and then let's draw so as x increases, we have to figure out what y is doing, and as x decreases, we have to figure out what y is doing. So let me grab my highlighter. As x is increasing, what's happening here? Y is decreasing. It's going down or decreasing. So y decreases. And then as x increases, as x decreases, that's this green, what is y doing? It's increasing. So y increases. If it's going up, it's increase. If it's going down, it's decreases. Okay. Key features of a graph. There are several things that your textbook mentions that are key features of a graph, and I'm going to list those here. Key features of a graph are its domain. So that's number one, the domain. The range is also a key feature of the graph. The intercepts, where it crosses the x and or y-axis. Whether it has symmetry or not, that is a key feature of a graph. The end behavior, that tells you a lot about what's happening with that graph, the end behavior of it. The extrema tell you a lot about the graph. The intervals of increasing tell you a lot, as well as the intervals of decreasing. And where the graph is positive or negative also helps give a clear picture of what the graph will look like. So domain and range. Remember, domain is how far, you can't tell I had an I there, how far left or right your graph goes, and your range is how far down or up the graph goes. The intercepts are where it crosses the axes, the x or y axis. Symmetry, line symmetry is what we've discussed in behavior. I want to point out something that hasn't been pointed out, and so a highlighter might come in handy. A graph is said to be positive in the area that the graph is in the green. It's talking about positive y values. So it's positive when it's in the green areas. And the graph is said to be negative when it's in the blue areas. I just wanted to point that out. And of course, intervals of increasing and decreasing, reading that from left to right, increasing till it gets to this relative maximum, then it's decreasing till it gets to the relative minimum, then it's increasing. So that's the intervals of increasing and decreasing. And I don't know why this is so blurry. I apologize for that. It says Mariana used the key features to sketch the graph of x as a function of y. Examine the key features in graph to identify which features Mariana graphed correctly and which ones she graphed incorrectly. So let's read those key features and see which one we can come up with that are correct and or incorrect. The first feature says that it's positive between x equals -3 and x equals 0. So let's see if that's true. Let's grab a highlighter. Positive between x equals -3. Let me count really quickly. -1, -2, -3. So -3 to 0. So yes, that graph is up here in the positive quadrants. And x is greater than 2. So if we go to 1, 2, x is greater than 2. Yes, I would agree that that is correct. So we'll go right correct there. that graph is positive in those areas. And again, those areas said from -3 to 0, it's definitely positive, and then from 2 forever. So this is a correct description of that graph. And then the next one, it's negative from x is less than -3. So here's -3. Is that graph down here in the negative area? Yes, it is. And it's negative between 0 and 2. Yes, I would agree with that, that it's negative down here in these areas. So yes, that one is also correct. Increasing for about x is less than -2. So x is less than -2. Let's see. Let me find x is less than -2. So -1, -2. Increasing. Okay, so I agree from here to here, it's increasing. And between 1 and 3. Only between 1 and 3 is it increasing? Between 1 and 3. Now, I agree it's increasing between 1 and 3, but it's increasing actually for x greater than 1. So I think this limits it, and so that one is not correct. That description is not correct. Okay, letter D, decreasing between x equals -2 and x equals 1, x equals -2, and x equals 1. I do think it's decreasing there. And for x is greater than 3. So for x is greater than 3, 1, 2, 3, it's saying that graph is decreasing, and that is not correct. Okay, it says the graph intersects the x-axis at -3, 0, -1, oops. Oh, sorry. -1, -2, oopsie. -1, -2, -3, 0, yes. 0, 0, and 2, 0. Yes, that is correct. It has a relative minimum at 1, -2. So 1, -2, is this a low point? Yes, that's correct. A relative maximum at -2, 4. -1, -2, 1, 2, 3, 4. I would agree with this one. And at 3, 2. 1, 2, 3, 1, 2. And that would be no. So that would make this statement incorrect. Or not correct, however you want to say that. And then for the end behavior, as x increases, so as x is increasing, y decreases. And that is wrong. Here. That is wrong. This one's okay. So this one is incorrect. Okay, so we went through those key features and we could see which ones that were incorrect there. And next, the number of people in line for a roller coaster throughout the day can be modeled by a function. Use the key features to sketch a graph of the function. And the graph is already sketched there for you, but let's look at it. It says, then interpret the key features if x represents the time in hours, since the ride opened at 10 a.m., and y represents the number of people in line. So I actually gave you the wrong thing. So let's see if we can come up with the key features from this graph. So we're kind of doing it in reverse, but that's okay. So let's look. This graph is positive from, and let's write this down. Positive from x equals -0.5 and x equals 12. Because as I look from -0.5 to 12, this whole graph is positive. So I'm going to put that. Okay, and then it's negative. when x is less than negative 0.5 and x is greater than 12. That's when it's negative. It's increasing for x is less than 1.4. So yes, as you look at that, from here to here it's increasing. So increasing x is less than 1.4. Let me write that. These are the places where it's increasing. X is less than 1.4. And where else is it increasing? It's increasing here. So that would be between x equals 5.3 and 9.9. And let's talk about where it's decreasing. So it looks like increasing, it's decreasing here, increasing, decreasing here. So it's decreasing between these two values. So that would be decreasing between x equals 1.4 and x equals 5.3. And then it's decreasing for values x is greater than 9.9. And that's here, 9.9. It's decreasing here. So 1.4 to 5.3, and then x is greater than 9.9 is where it's decreasing. Intercepts. Oops. Sorry about that. Okay, where does it cross the x-axis? It crosses at negative 0.50 and 12, 0. And then those are x-intercepts. The y-intercept, there's only one, is right here, so 0, 200. Relative minimum. I hope you all have enough room to write all this. I think you do. Relative minimum would be here, and that is 5.3, 133. Relative maximum is here. Oh, actually, there's two of them. Here's one relative maximum. Here's another one, because in those two areas, that's where there's not a point higher, so there's two of them. 1.4 is the first one, 448, and 9.9, 643. So those are the ordered pairs for that. And then the end behavior, as x increases, so let me highlight. As x increases, y decreases. And then as x decreases, y decreases. As x decreases, so does y. And that's all the key features from that graph. And I apologize for not having those key features there so we could actually graph that picture. Then the last one, example 8. Hawkeye is a computer system used in tennis to track the path of the ball. It is used as an officiating aid to locate the landing spot of a tennis ball when players challenge a call. Use the description and graph of a player's forehand and backhand shots to compare the pass of the two shots if y is the vertical height and x is the distance. So obviously I did not copy down the description, and that's okay. And I don't even think the full graph is there. And I truly apologize for that. So the full graph, like this is the y-intercept, 0, 2 is our y-intercept. And then this graph comes down, and the x-intercept is 70, 0. This graph is going by tens. So this is 10, this is 20. So if you'll just draw that in, I'm so sorry. 30, 40, 50, 60, there's 70, 80, so on and so forth. Now, the description says, during the forehand, the ball leaves the player's racket at a height of 2.8 feet. So does that look correct? Does that look like the ball is at 2.8 feet? Yes, and I was wrong when I said 0, 2. So obviously that y-intercept is 0, 2.8. And travels 29 feet when it reaches a height of about 10 feet. So 29 feet and it reaches a height of about 10 feet. So 29 feet, 29, let me grab my pointer. 29 would be about here. Is that true? So, actually the verbal description, in that verbal description, which I'm so sorry it's not on your paper, compared to our graph, the maximum height in the verbal description is 10 feet when x is 29. Is that the maximum height here? The maximum height here is 7 feet when x equals 35. Because see, this is where it's occurring. 7 feet when x equals 35. And my graph is kind of crooked, so it's hard to tell there. So that's a big difference. And the x-intercept of the backhand is 70, 0, is 70. And the x-intercept of the forehand is actually 58 because it says it hits the ground 58 feet from where it was hit. So this ball hits the ground at 70 feet from where it was hit, and then this one hits the ball from 58 feet. Oh, I can tell something else I goofed up from what I read. The description says 2.8. This actual graph, it's 2.5. And so our y-intercepts are different. So this was x-intercept, and this is max or extrema, and our y-intercept is different. Our y-intercept for the description that I've read to you is that it's 2.8 feet high, and our graph is actually 2.5 feet high. And then we're not going to write this out, but it does increasing and decreasing changes because our maximum value changed. Looking at the graph, it's increasing until it gets to 7 here, whereas with this one here, it would be increasing until it gets to 10. So the increasing and decreasing values would actually change for that verbal description compared to the graph description. So I apologize if that was kind of sketchy, but I think that you got the gist of what we're trying to say here. I hope you have a wonderful day.